Now, before we have a look at our next theorem, we want to consider something that we call the alternate segment. So the alternate segment here is one where we have a tangent to a circle, and then we have an angle that's created by the chord, a chord that's drawn in the circle, and the tangent. Now, remember when we draw a chord in a circle, we cut our circle into two parts, and those two parts we call segments. So if we have a look at the major segment we've got here, and then the minor segment there. So what we do once we create BCQ, this angle here, then what we create is what we call the alternate segment. The segment that's related to BCQ is the one that's unshaded, that small one. The other segment we call the alternate segment. So that's where the term alternate comes from. It's the other segment, as alternate means, other one. So in this case, no matter what BCQ is, the shaded part here is the alternate segment. So we're creating two segments, and the angle that we have is in the other segment. So there's our alternate segment there. So we get that idea. Now, what's the theorem going to be relating to in this one? Well, let's have a look. I've created tangents from a circle. So C, a tangent, CD is a tangent there. So it's touching at that point. And I've created an angle here, CDB. Now my alternate segment here, so I've got the segment that's related to CDB here. So that would be one segment. The other segment is here. Now, the other segment in that, I've drawn an angle to the circumference in that one. So in that segment here, we've got an angle, and if you have a look at the angle, I'm moving the angle around, but you notice it's not moving. And we know that. We know if we have a chord that's a particular length, that the angle in that sits on that chord, that's subtended by that chord, won't change. It's always the same. But if you're also looking at our alternate segment, well, the angle created by the segment and the angle in the alternate segment, that is the same, 64.64, 64.64. That is exactly the same. Now, if I move my tangent, which creates a different angle here, look what happens. Our angle in our alternate segment changes, because once I move the tangent here, my length of my chord changes as well, and so it doesn't, and that moves as well. If I change the size of my circle as well, you can see the angle starts to change and moves. I'm moving the point B around again, which changes the size of our chord, but it changes the size of the angle here, and that angle will stay the same every time, that angle in the alternate segment, and we can again move it around. It doesn't change. So how do we get this theorem? How do we prove this one? Well, it's a little bit harder to prove here. So what we've got O is the center of a circle, and PQ is the tangent. It contacts the circle at C, and we want to prove that the angle here, BCQ and CAB are equal. Now, what we want to do is construct our diameter here. So we're going to construct diameter. So CM becomes the diameter, and we're also going to construct MB, so the point there. Now we know, because it's a diameter, MC is perpendicular to PQ. So we know that's the case. So we know MCQ is 90 degrees. So BCQ would be 90 minus MCB. So this angle here. So that would be, this angle is 90 minus that angle. Now, we know that from our angle in a semicircle, so because it's got the diameter, the angle in the semicircle is 90. So if that's the case, we know these three angles add up to be 180 degrees, because it's the sum of the angles in a triangle, which means that CMB must be 90 minus MCB as well, this angle here. So this angle's 90 minus this angle, and this angle's 90 minus this angle, which means those two angles that we've got there must be equal. So we've created those two, which must be equal. Now, if you remember, BC subtends that angle at the circumference M, but it's also subtending that angle A there at the circumference. Now, angles at the circumference subtended by the same chord are equal, which means that angle becomes equal there. So BCQ is equal to CAB, which means the angle in the alternate on the circumference in the alternate segment is equal to the angle that's created by the chord and the tangent. So that's what that theorem is stating. And remember, we saw it in our diagram before. Whenever we move that point around, it doesn't really matter where it is, it stays the same because it's the angle subtended by that chord BC. So there we go. That's what we call the angle in the alternate segment theorem. So we can quote that. So the angle in a tangent between a tangent and a chord and the point of contact is equal to the angle in the alternate segment there. It's long-winded, but really powerful theorem and some nice mathematics that goes with it.